No, I don't have it. Hinok has one. Yeah. At some examples, let's do NH3. This is called ammonia. Ammonia is something that you would smell this if you're getting your hair dyed, okay, or hair permed or straightened, or Windex. You know when you clean the windows, you know the smell of Windex? You can smell that? That's called ammonia. And actually in organic chemistry, there is a lab where you're supposed to identify smells. Just by smelling, you're supposed to identify what chemical is in there. So you could imagine, right? People would be wafting chemicals like this. Like remember, you're not supposed to take a chemical, directly sniff it, right? It could kill your brain cells. Yeah, it's poisonous. So you take it about a foot away in front of you and you waft the air towards you. And there's a lab where you just smell chemicals that way and you could identify the chemicals in it. So this one is a unique smell. It's called ammoniacal.
I did that with hydrochloric acid.
Oh, yeah. So you could tell right away.
I didn't know that was pretty brutal.
Yeah, and it could really hurt your nose after a while too. Yeah. So this is a very distinct smell. So ammonia. What do you think is the central atom for this one? Now, you know the central atom will be the one that is the least electronegative or the only one, right? So the central atom, in this case, will be nitrogen. But first, we need to look at the number of valence electron. The number of valence electron, right? So, nitrogen is 5. And how many nitrogen do you have? Only one, imaginary one there. Hydrogen, 1 electron times 3. So, 5 plus 3, you have 8 valence electrons. So that's what we're going to draw. Okay? Is that okay so far? All right. We get all these from the periodic table atomic number. Okay, so now we put N in the middle. And then let's look at the electrons. The valence is 5, right? So we go 1, and we go all around 2, 3, 4. And then you can choose anywhere where you want to put the second one. I'm going to put it right here. Okay, so we got 5. And then you have hydrogen. So where do you think you'll put hydrogen? It depends on where you're missing. Can I put hydrogen right here?
No.
No, that's full. So hydrogen is going to go right here. And how many does hydrogen have? 1. So look at this. The orange hydrogen has 1 electron with it. And you need another 2 more hydrogen here with the electron that it carries. And the hydrogen right here, and it has 1 electron with it. Okay, because remember hydrogen carries 1 electron, but you have 3 of them. So now you count. How many can hydrogen have? Maximum of 2, because it's a small element, right? It cannot follow the octet rule. It just can't have 8 because that's all it has, right? So hydrogen is happy. This hydrogen is happy. This one too. They're all stable. Look at nitrogen. Nitrogen can do octet rule. Should have 8. So you count 1, 2, 3, 4, 5, 6, 7, 8. And then it's done. So if you look at this structural configuration of this, how many single bonds will you have? 3. Now, hydrogen here, hydrogen there, and hydrogen there. Now what about these 2 electrons right there? Because you can't really move. See, in the other examples that we had, remember electrons will move because this is not that stable, right? It's not that stable. So the electron will move and form a double bond. Here you can't. You can't in this case, okay? Because hydrogen is full. Hydrogen's going to say, no, I don't want this electron. This electron should move here, but no, it can't. So that's it. So you'll have the loose electrons right here, and this will make it a polar covalent, which we don't have to worry about the names right now. All we know, and you need to know, that the hydrogen can only hold 2. And you can't have a double bond here because hydrogen can have a maximum of 2 only, okay? So that's it. It's done. So that makes it loose electrons on that side. But if you have something like N2, can you try N2? Oh, that's just nitrogen by itself. So then you go, do you have a central atom for this one? No, they're equal, right? So, how many valence do you have for N? 5, but how many N's do you have? So, you're going to draw 10 electrons, right? We'll see. Okay, so you put your N here. And how many does it have again? 5, right? So you go 1. I'm just going to draw the electrons all around and then we'll make them move if they need to. 1, 2, 3, 4, and then one more. I'll just put it right here, 5. Okay? And then you have the other one right here. I'll draw in pink. Also has 5. So 1, 2, 3, 4. So that's good now. And 5. I'll put it right there. It doesn't matter where you put the 5th one. Okay, so now if you count how many electrons or dots each nitrogen have, do you think they're happy? 1, 2, 3, 4, 5, 6. No. 1, 2, 3, 4, 5, 6. No, none of them are stable. So here we go. Look at this. You see this loose electrons there? They're gonna try to make this stable. This electron is gonna move right there. It's there now. So that's gone, right? And then this one of these electron, this one here, it will move here too. So that's gone. But then if you count, how many do they have? 1, 2, 3, 4, 5, 6, 7. Still not good. So guess what's gonna happen? You see that lonely electron right there? It will move here. So there you go. Gone. See this electron right here? It will move here. That's gone. Okay, so let's take a look. So how many do you have now? 1, 2, 3, 4, 5, 6, 7, 8. Count the pink nitrogen. 1, 2, 3, 4, 5, 6, 7, 8. So do you think those loose electrons need to move?
No.
How many bonds maximum can you have? You can only have 3 bonds, by the way. You can only have a triple bond. So if you draw this, N, you see you have 1, 2, 3, 4, 5, 6. Remember, 2 electron equals 1 single bond. So 6 electrons is gonna be how many bonds? 3. 1, 2, 3. And then you still have those loose electrons. We're gonna keep them here and there. That would be the more stable configuration they'll have. Now the electrons can be here, but then the electron will move to the other side to balance it out. So that would be the structure of N2. And guess what? This is what you're breathing in right now. This N2, 78% of the air around you, right around here. When you take a breath, go ahead, take a breath, deep breath. There you go, N2 into your lungs. You just did. That's what you have. One more example with the Lewis dot. What about O2? Okay, I lied. One more after this one. So 2 more. We'll do O2, and I want you to do H2O, okay? I'll give you 2 minutes to do that. Go for it. So, step 1, find out how many valence. Look at the periodic table. How many on the outside? Does everyone have the valence electron for oxygen? People on this side. How many? 6. Okay, good. So 6 times 2. You have to draw 12 electrons, right? Okay, so you put O. So you put 6 each. See what yours looks like. 1, 2, 3, 4, 5, 6, and then another O. And B, I'm going to use X's here. 1, 2, 3, 4, 5, 6. Okay, so and then you count how many they have around. 7, right? Not happy. So what's going to happen? This loose electron gonna go here. That's gone. That's gone. And then that loose electron is gonna go right there. That's gone. Okay, so now how many? 1, 2, 3, 4, 5, 6, 7, 8. Remember, this is gone. 1, 2, 3, 4, 5, 6, 7, 8. So what does oxygen look like? Now, do you think those loose electrons are gonna need to move? They can't. They don't need to, because if this moves, that's gonna be unstable. You don't want that unstable. The electrons are more stable if they're paired up. So this will be a double bond, like that, with how many loose electrons? 4 each, right? Like that. So this is what oxygen would look like, and they're not gonna form a triple bond because that will make it unstable, and you can only have maximum of 3. So that's what it will do. This is what we're breathing in. 21% of this air is oxygen. And then water, there's also water in the air. You know, when you breathe out, you're actually breathing out water, and you don't see that. But if you go to the window when it's cold outside and you go on the window, you guys see smoke, and you go outside and you look like you're smoking, right? When you blow, you see the smoke. That's water. We just can't see it here, but you are giving off water. So go ahead and draw the Lewis dot for water, and then we'll move on to the dividing chemical formula. How many valence here? 1 times 2 and 6. So 6 plus 2, 8 altogether, right? We good? Okay, so what do you think is the central atom? Oxygen in the middle, because there's only one of it. So O in the middle, and it has 6. 1, 2, 3, 4, 5, 6. And hydrogen, only one. So you see, I automatically put the electrons on the outside because hydrogen can only hold 2. So that's where hydrogen will go when there's only one electron. And that's it. So if you look at this again, you'll have 2 loose electron. That makes this again a polar covalent. Again, we don't need to know the names. But if you have loose electrons there, the tugging. You guys remember the video yesterday of the dogs fighting over the ball? One is a stronger tug, one's pulling harder, right? That's called a polar covalent. But don't worry about the name. I'm teaching you advanced stuff. You don't need to know that part. But that's how you do the Bohr model, the Lewis dot. Sounds good? Sevi? Huh? Yeah, the oxygen right here. Okay. 2, 4, 6, 8. Yeah, that's a double bond. You want me to go over this one? Explain this? Okay. So you see how oxygen is actually O, right? So you have 6 each. So you have 12 electrons in total that you need to draw. So when you put this here, I'm going to draw it right here. So oxygen has 6 plus 6, 12 electrons in total. So when you do this, you're going to put 1, 2, 3, 4, 5, 6 each, right? And then you do 6 for the other one as well. 1, 2, 3, 4, 5, 6. So you see, those are very unstable. The single electrons, those are the first ones that will move. So this electron here, that's going to be gone. It will move here. That's gone. Okay. This pink one, very unstable because it's solo. That's going to be gone. It's going to move here. Make sense? So what we have now is you have these two here, and then you go, if I move this one over there, one has to move from the other oxygen. But that's going to make this a single dot. That's going to make it very unstable. They're not going to do that. So they're going to stop. That's it. So these ones will remain on the outside as loose electrons. And you'll just have a double bond of oxygen with the dots on the outside.
Can I ask a question?
Of course.
How do you come up with the electrons again?
The number of electrons. Okay, on the periodic table, okay, oxygen, you'll have 2 numbers, 8 and 16. You have that one there. Sometimes it's like a decimal point, right? So this one here, that's the atomic number. Okay, guys, review for the quiz tomorrow. You should know when you look at the periodic table, you have these 2 numbers, one a smaller number and one is a larger number. This is called the atomic number, which tells you the proton, which is equal to the electron. Okay, that's the number that will tell you for the total number of electron of that atom. And this one is the proton plus neutron. This is called the mass number or the atomic mass. Okay, so when you're drawing the Bohr model, you have to draw the entire thing, 8. So I'm going to review that as well. So the Bohr model for oxygen, again, tomorrow you'll get questions like this. you have to put the P and the N inside. So that number is the number of proton. And the number of neutron will be the big number minus the small number. So 8 as well. And then this will be 2 maximum. Now, this answers your question directly. How do we know the number of valence for the Lewis dot? It's the ones on the outside. So 2, and you only have 6 to make it 8, right? Because you need 8 electrons. This dots right here, that's the one that goes onto the Lewis dot. So here's the Bohr, and here's the Lewis. 1, 2, 3, 4, 5, 6. And again, does not matter where you put the dots as long as they're paired up. 2 in each of the 4 corners. Okay? Sounds good?